Today I want to talk about how to rationalize the binomial denominator if you have a radical in it. Before I do, this should look familiar to you. This is the last slide or the last piece of the last video, but because this is where we're going to use it and it's going to become very important when rationalizing binomial denominators, I just want to review it really quickly. Remember, a plus b times a minus b is going to give you a squared minus b squared. Therefore, the square root of a plus the square root of b times the square root of a minus the square root of b is the square root of a squared minus the square root of b squared. Well, square roots and squares cancel, giving me just a minus b. So if I look at it with numbers plugged in as opposed to letters, looking at just this one example, excuse me, I don't need to use FOIL because I can use my formula. So notice that my a is 3 and my b is the square root of 7. So applying the formula, I have a squared minus b squared. Well, that gives me 9 minus 7, or 2. So I kind of addressed this in the last video. Where is this going to be helpful? Well, this is going to be helpful when I need to rationalize a denominator with a binomial, because notice that I can get rid of a binomial with a radical by multiplying it by its conjugate. Once I multiply by its conjugate, I do end up with just a number. I no longer have a radical expression. So we've learned two ways to rationalize denominators. So we've learned one, we're in the process of learning another. Because remember, we cannot have radicals in the denominator. If we have a monomial radical in the denominator, that is when we multiply top and bottom. My and got crazy there. Top and bottom by the monomial radical. Because remember, when I multiply two monomial radicals together, for example, say the square root of 13 times the square root of 13, I end up with just 13, because in essence what I get is the square root of 13 squared, which then reduces, like I said, just down to 13. So whatever is inside of that radical expression comes out of the radical expression, no longer has a radical. If we have a binomial radical in the denominator, now I'm going to multiply top and bottom by the conjugate. And when I say top and bottom, I'm talking about top and bottom of the fraction, since I'm talking about having something in denominator. Because as we just saw up above, multiplying by a conjugate gets rid of radicals. So let's look at this first example. So I noticed that I have the square root of 15 in the bottom, which is not okay. So I'm going to need to, according to up here, I'm going to need to multiply by the conjugate. Well, all the conjugate does is change the middle sign. So I get 4 plus the square root of 15. If I do it to the bottom, I have to do it to the top. Because I'm multiplying the whole top by this conjugate, I have to use parentheses and FOIL, or distribute, however you want to think of it. 6 times 4 gives me 24. 6 times the square root of 15 is plus 6 square root of 15. Square root of 15 times 4 is plus 4 times the square root of 15. And the square root of 15 times the square root of 15 is a positive square root of 225. 15, kind of depends how you look at it. Square root of 15 times square root of 15 is just 15. All over. On the bottom, I can either FOIL or distribute or use the formula. I'll get the same answer either way. I'm going to use the formula because it's faster, and I get 4 squared minus the square root of 15 squared. Well, on top I have a set of like terms I can combine. I can combine the 24 and the 15. I can also combine the 6 square root of 15 and the 4 square root of 15, giving me 39 plus 10 square root of 15 all over 4 squared minus square root of 15 squared, so 16 minus 15, so 39 plus 10 square root of 15. I could say all over 1, it's not necessary to put it over 1. Looking at a few more examples. Example 2, I'm going to go ahead and do the same thing. I believe there are just these 3 examples. Multiplying by the conjugate of 10 plus the square root of 7 is 10 minus the square root of 7. I hit something, so I don't know if this recorded, so let me review what I did. I saw that I had 10 plus the square root of 7 on the bottom, so I noticed I'm going to have to multiply the bottom by the conjugate, which is 10 minus the square root of 7, which means I'll also have to multiply the top by 10 minus the square root of 7. So going ahead and multiplying the whole top, 3 times 10 is 30. 3 times the minus square root of 7 is minus 3 square root of 7. Also distributing the next one, minus 2 square root of 7 times 10 is minus 20 square root of 7. Minus 2 square root of 7 times minus square root of 7 is plus 2. Square root of 7 times square root of 7 is just 7 times 7. All over. On the bottom I can FOIL, or I can use my formula. I get 10 squared minus the square root of 7 squared. I'm going to clean up the top a little bit so I have some like terms. I can also multiply 2 and 7, giving me 30. Negative 3 and negative 20 is negative 23 square root of 7. And then plus 2 times 7, which is 14. And on the bottom I get 10 squared, which is 100, minus square root of 7 squared. They cancel, giving me 7. I can combine the 30 and the 14, giving me 44 minus 23 square root of 7, all over 93. And that's the best I can do. Nothing else I can simplify. Looking at the next example, this would be a good one for you to pause the video and try it before continuing on. Okay, so now that you had a chance to try it, I'm going to go ahead and multiply the bottom by the conjugate of 2 plus the square root of 6, meaning the top also has to multiply by 2 plus the square root of 6. And I do have to multiply the whole top, so I'll use parentheses. So first times first is going to give me 8. Outside times outside is going to give me plus 4 square root of 6. Inside times inside is going to give me minus 6 square root of 3. Last times last is going to give me minus 3 square root of 6 times 3, which is 18. On the bottom I can use this formula, 2 squared minus square root of 6 squared, or I could distribute if I can't remember it. Then from here I have no like terms on top, because remember they have to have the same radical part. I can take out a square root of 9 from here, and I can simplify the bottom. Square root of 7. So this becomes minus 3 times the square root of 9 times the square root of 2, all over 4 minus square root of 6 squared cancels to be 6. And now, just cleaning up a little bit, this is going to become 3 times 3. And on the bottom, I'm going to get negative 2. If it happened that every single term could be divided by negative 2, I could reduce, but every single term can't, since a negative 9 can't, so it stays like this. These are not like radicals. This is my final answer. And I believe that was just that one. Yep, so that's the end of the examples for rationalizing denominators with binomial radical expressions.